Good evening, ladies and gentlemen. I'm Shauradip Basu from Group 4, and our topic is life cycle analysis of slurries in a CMP process. Okay, so to begin with, why did we select this? Well, because there's a very famous paper from Sara Boyd where she has some values published wherein she says that the CMP polishing solution, it generates or rather it requires an energy intensity of 17 megajoules per kilogram and a carbon intensity of 1.4. But like everybody uses this like a postulate, like nobody has challenged or for that matter even questioned it. So we have decided that like what's the reasoning behind these values? Where is it coming from? So next slide, please. Yeah, so for the CMP process, we need silica nanoparticles. Now, we have three main routes to generate this. Number one, pyrolytic. Number two, precipitated. And number three, purified stover, or as it is known as TIOS. Next slide, please. So here, from the first route, which is the pyrolytic silica. So in order to generate this, we need silane. That's the main component here. So as you can see from the table here that it corresponds to around 17.136 GWP, and the other input that we require is hydrogen. So that also corresponds to a global warming potential of 0.75 kilograms of carbon dioxide per kg. And lastly, we have energy, which is majorly generated from natural gas. That also has a significant amount of GWP, around 1.26. That in total, that corresponds to 19.14. Now, my colleague will throw some more insights.
Next slide, please. So I will now continue with the precipitated route. There we have other input values, mainly the sodium silicate, sulfuric acid, water, and electricity. And we see here that the main ingredient is the sodium silicate regarding the GVP. And additionally, the electric power that is used in the process. And we come out in a lower value range of 3.951 kg CO2 equivalent per kilogram silica nanoparticles that are being produced. And next slide, please. And this third route that is used in the industry is using the Stöber process, mainly enabled through the TIOS input. And this is the main contributor with our calculations with an amount of 17.66 kg of CO2 equivalents and a sum of 19.6 24 and some else kg CO2 equivalent. So to conclude those routes, that for the nanoparticles itself, it's in the same range, the purified Stöber and pyrolytic route. So, and the best route would be precipitated production of silica nanoparticles. Next slide, please. But this is not everything that is coming into a slurry. We need additionally chemicals and water. And if we then account for those inputs as well, we can see the amount of CO2 equivalent per kilogram of slurry on the right side in the plot. There is a distinction between the chemically dominant slurry and a mechanically dominant slurry. The chemically dominant slurry is, in our findings, way lower due to the fact that we use way less of the nanoparticles. And the slurry using more of particles, so the mechanical dominant slurry was in a range from 0.633 to 2.437 kilograms of CO2 equivalents. And we found out with our calculations that are based on some assumptions that we come out in the similar range of magnitude as the value of Sara Boyd. Next slide, please. To conclude, the silicon nanoparticles, as mentioned already, had the most impact in the CMP slurry. And we found out that participated silica have the least impact if you have a slurry that is based on this synthesis route. And as well that the chemically dominant CMP slurry is also lower with a GVP impact than the mechanically dominant slurry. But our values generally aligned with Sara Boyd's value, though there is some lack of information that was filled out with some assumptions. Our input values and calculations were based on values out of the chemistry industry. And we know that higher purity requirement is within the semiconductor industry, but those values aren't really published as far as we could have found. And one example would be we used the TIOS value in the Stöber route. It was around 5 kg CO2 equivalent. And if you look at the Sara Boyd publication, you see she mentions that TIOS in the semiconductor industry has more around like 100 kilograms of CO2 equivalent. So this would be a change in magnitude. And if we look at solar grade silicon and microelektronik silicon, we can also see the CO2 equivalent impact is also in a magnitude range. So it's fair to assume that this value that we calculated has also the possibility to be as high as 10 times higher. So take it with a grain of salt. That's fast.